In the previous lecture, we were examining high Peclet number transport past a mobile surface, where the velocity tangential to the surface is non-zero at the surface. We had obtained the correlation for the flow past a bubble, and there we found out that the Sherwood number is proportional to the Peclet number to the half. Okay. For a rigid surface, it was p e power 1/3. In this case, for a mobile surface, it is proportional to p e power half. The difference is because in this case, the tangential velocity is non-zero at the surface, whereas at a rigid surface, the tangential velocity was constrained to be 0 at the surface. And we were solving the equation for a general flow field, okay, where the tangential velocity is some function of x. Okay, and from the mass conservation condition, the normal velocity has to increase linearly with x away from the surface. Okay, this comes out of mass conservation, where this should be the surface velocity and not Vx. Okay, so this should be Vs and not Vx. Okay. Substituted that into the equation, expressed in terms of the similarity variable, and then simplified, divided by the prefactor of the diffusion term on the right, and this was the equation that we had obtained. The red part is the dependence of the concentration of the similarity variable. The blue part is the dependence of the boundary layer thickness on x. The red part we had already solved to get the solution for the concentration field, okay, which was the same as what we had for the flow past a bubble, and which is also the same for what you would get for the falling film if you used this procedure to do the calculation. Okay, so that procedure is the same. The blue part is equal to 1, and that has to be used to determine the boundary layer thickness. Okay. I can rewrite the blue part as Vs by 2d d delta x square by dx plus delta x square by d dVs by dx. This is equal to 1. And divide by the prefactor of the first term on the left to get a first order inhomogeneous equation, okay, is equal to delta x integrating factor is equal to e power integral dx into 2 by Vs dVs by dx. Okay. Okay. 2 times log the natural log, okay, okay. 1 by Vs dVs by dx is the derivative of the logarithm of x. Okay. So, this is equal to e power 2 log of Vs, okay, is equal to Vs square. Okay. Therefore, you will get delta x square is equal to c by Vs square plus 1 by Vs square integral 0 to x dx prime, okay, 2d by Vs of x prime into Vs square. Okay. So, that is the final expression for the boundary layer thickness. If we assume that delta x is equal to 0 at x is equal to 0, that is we start the boundary layer measurement at the location where the heating starts or where the change in concentration starts, that is if delta x is equal to 0 at x is equal to 0, then the expression for delta x square is equal to 2d by Vs square integral 0 to x dx prime Vs of x prime. Okay. So, this is the final expression for the boundary layer thickness for this particular case. So, for any general two dimensional flow, this can be used in order to determine the boundary layer thickness. Okay. So, let us take an example, okay. And the example we will take is for the boundary layer flow in an extensional flow of a polymer filament, okay, which is being cooled. Okay. So, the configuration is as follows. Okay. You have a filament, okay, in extensional flow. Okay. This diameter is d naught. Okay. At the start of the filament, the diameter is d naught. Okay. And it is coming down with a velocity v naught. Okay. It is coming down with a velocity v naught. Okay. The temperature, okay, at the surface T is equal to T naught, and here within the film T is equal to the fluid temperature. Okay. So, this is a polymer film that is being extended, and the velocity Vx is equal to V naught plus k times x. Okay. Okay. So, I take a local coordinate system here. Okay. Okay. So, the velocity profile is very close to a plug flow, okay, and the local velocity is a function of the location x downstream. Okay. As the film is falling down, the film is being pulled, and therefore, the velocity increases proportional to x. Therefore, here Vx is equal to V naught plus k times x. Okay. And my objective is to find out the heat flux, the average heat flux in the Nusselt number for this particular case for a film which has a length L, okay, for a film which has a length L. Okay. What is the film thickness? Okay. We know that delta x square is equal to 2d by Vs square integral 0 to x dx prime Vs of x prime. In this particular case, Vs is V naught plus Kx. Okay. In this case, Vs is equal to V naught plus Kx. Okay. So, I can write this as 2d by V naught plus Kx the whole square integral 0 to x dx prime V naught plus k times x prime. Okay. Note that this k is the extension rate. Okay, this is the extension rate, not to be confused with the thermal conductivity, which I will be writing with a small k. Okay, so, this is the extension rate, not to be confused with the thermal conductivity, which I will be writing with a small k. Okay. So, this can easily be simplified to get d into V naught plus kx the whole square minus V naught square divided by V naught plus kx the whole square. And there should be a 1 over k as well. Okay. And since this is a heat transfer problem and not a mass transfer problem, I should write this as the thermal diffusivity alpha instead of the mass diffusivity. Okay. So, integral of kx, you will get kx square by 2. So, there will be a k coming out. Okay. So, it will be v naught plus kx the whole square minus v naught square divided by k into v naught plus kx the whole square. Okay. So, that is the expression for the boundary layer thickness. Okay. This is just obtained from this 2-dimensional solution. Okay. This is straight away obtained from this 2-dimensional solution by just substituting for delta x in terms of the surface velocity. Okay. Of course, the assumption in this case is that the boundary layer thickness is much smaller than the diameter of the filament. Okay. As it is coming down, the boundary layer thickness is much smaller than the diameter of the filament. That is the assumption here. Okay. So, how do we find out the heat flux? Okay. We know that the heat flux Q, Qz, perpendicular to the surface. If I take a local coordinate system where this is z perpendicular to the surface and the x direction is along the flow direction, Qz is equal to k into T naught minus Tf, divided by delta x root of 2 by pi. Substituting the values here, I will get k into T naught minus T infinity. Okay. I should write this as Tf here. Okay. Into root of 2 by pi. Okay. 1 over delta. So, I will get 1 over, note that this whole thing is equal to delta square. Okay. This whole thing is equal to delta square. I have to take 1 over delta. So, I will get 1 over square root of k by alpha. Okay. Into v naught plus kx by square minus v naught square whole to the half power. Okay, that is 1 over delta x. The average flux Q average is equal to 1 by L integral 0 to L and dx times Qz, which is a function of x. And this integral can be done, right. You take you substitute u is equal to v naught plus kx the whole square minus v naught square, du is equal to 2 into v naught plus kx into k. Okay, derivative times dx. Okay. If u is equal to v naught plus kx the whole square, du is by dx will be equal to 2k into v naught plus kx. Okay. So, that you can substitute. Okay. So, this will be equal to k into T naught minus Tf by L root of 2k by pi alpha. And I have this u power minus half, u power minus half. Therefore, I will get 2 times u power half here. I will get 2 times u power half. And if I do this integral, I will get plus k L, okay, whole square minus V naught square whole power half by k. Okay. And you can do some algebraic simplifications here. Okay. You can simplify this a little bit, okay, to get k into T naught minus T f by L, okay, into root of 2k by pi alpha, okay, into root of L into 2 V naught plus k L, okay, by k. Okay. So, this is the expression for the average flux. Okay. This is the expression for the average flux. Okay. I have skipped a few steps here, but you should be able to do it quite easily. Okay. So, that means that here V naught plus k x dx is equal to du by 2k. Okay. So, I put du by 2k and then u power minus half in the denominator. I get 2 times u power half, okay, and that 2 and this 2 will cancel out, okay, and I will get a 1 over k ultimately, which is basically this term here. Okay. So, I will leave that simplification for you. So, this becomes k, and the Nusselt number is equal to q average by k. This is the thermal conductivity, not the extension rate, k into T naught minus T f by L, okay, is equal to square root of L into 2 V naught plus k L. Okay. There is a factor of 2 here. Okay. So, okay, divided by pi alpha whole to the square root. Okay. So, this is the Nusselt number correlation. Okay. It depends on the velocity V naught at the start of the filament drying process, the velocity V naught at the start of the filament drying process. Okay. The velocity at any location is V naught plus k times x. So, the correlation depends upon V naught, it depends upon k, and it depends on the total length divided by alpha. Okay. K times L has same dimensions as velocity, and V naught times L has same dimensions as the thermal diffusivity, because of which you get this Nusselt number correlation, okay, for this particular case. So, implicit in this calculation is the assumption that the boundary layer thickness is much smaller than the diameter of the filament. Okay. The diameter at any location d is much larger than the boundary layer thickness, so that I can consider this to be diffusion into an infinite medium. That is implicit in this calculation. Okay. When, under what conditions is this assumption valid? Okay. So, if I have a cylindrical filament, right, then just from mass balance, from the conservation of volume, the volumetric flow rate at any cross section has to be the same. Okay. So, if I have diameter d at some downstream location and d naught at x is equal to 0, if the diameter is d naught at x is equal to 0 and it is d at some downstream location, okay, then I require that pi d naught square times v naught, the initial velocity, is equal to pi d square times v square. Okay. Into v naught plus k L the whole square. I am sorry, there is no square here. Okay. The flow rate is the cross sectional area times the velocity. Okay. The perpendicular, the volumetric flow rate is a cross sectional area times the velocity. Okay. Which means that d square, the diameter at any location in the film, is equal to d naught square V naught by V naught plus K L. That is the diameter of the film at some downstream location L from the start of the drawing section. Okay. And we require that the boundary layer thickness be much smaller than this diameter. Okay. Recall that delta x square was equal to this one. Okay. Delta x square was given by this. Okay. The whole square. Okay. So, if I take the ratio delta x square by d square, okay, I will get alpha into V naught plus K L the whole square minus V naught square okay, into V naught plus K L by d naught square V naught. And these two can cancel out and you will get alpha. Okay. I can expand this out. Okay, so okay, there was a mistake in the brackets here. This should be here. Okay. And these two terms will cancel out. Okay. So, I will get this is equal to K L the whole square plus 2 V naught K L. So, this is the ratio of the square of the boundary layer thickness and the diameter of the filament at some downstream location. Okay. I can write this as L by d naught into alpha into 2 V naught plus K L okay, by d naught V naught into okay. So, that is the final expression for the ratio of the boundary layer thickness and the filament diameter. And for the boundary layer approximation to be valid, this has to be much smaller than 1. Okay. For the boundary layer approximation to be valid, this has to be much smaller than 1, which means that L by d naught has to be much smaller than alpha by d naught V naught okay, into 2 V naught plus K L by V naught plus K. Okay. So, that is the condition under which the boundary layer approximation is valid. Alpha by d naught V naught is a Peclet number. Okay. It is the inverse of a Peclet number based upon the diameter and the velocity. Okay. Alpha by d I have written it the other way around, my apologies, I have written it the other way around. So, this should be d naught V naught by alpha okay. and over here it should be inverse of what I had there, 2 V naught plus K L. Okay. Note that d naught V naught by alpha is equal to a Peclet number, okay, based on d naught and V naught. Okay. So, the condition for the validity of the boundary layer analysis is that this Peclet number is large compared to 1. The second term here, okay, the second term here is approximately 1. Okay. So, it is equal to a half if K L is much smaller than V naught, and it is equal to 1 if K L is much larger than V naught. Okay. So, it is approximately equal to 1. Okay. Therefore, you require that the length by diameter has to be much smaller than the Peclet number in this case for the boundary layer approximation to be valid. Okay. It has to be much smaller than the Peclet number. As you recall that a similar condition was also derived for the falling film case, okay, when there was a film that was falling when we studied similarity solutions, we found out that the length to thickness has to be much smaller than the Peclet number in that case for the boundary layer solution to be valid. A similar condition applies here. Okay. So, this illustrates for you how this method of boundary layer analysis can be used even in cases where the velocity is a function of the downstream distance. Okay. In cases where the velocity is a function of the downstream distance, we know what is the surface velocity, we know what it is its variation with respect to x, and in order to get the boundary layer thickness, all we need to do is to substitute that velocity field into these expressions, okay, for the boundary layer thickness for a 2-dimensional flow. Okay, just substitute into these expressions, and from that you will get the boundary layer thickness straight away. The heat flux goes as 1 over the boundary layer thickness, and the average flux is 1 over L times integral 0 to L of the heat flux, local heat flux. So, we just have to carry out that integral, substitute the boundary layer thickness into that expression, and derive what is the correlation for the Nusselt number or the Sherwood number. So, this completes our analysis of boundary layer theory for the flow around surfaces, flow past surfaces in the limit of high Peclet number for both rigid surfaces as well as for mobile surfaces. For rigid surfaces, the Nusselt number or the Sherwood number are proportional to Peclet number power 1/3, because the tangential velocity is 0 at the surface. For mobile surfaces, it is proportional to Peclet number power half, because the tangential velocity is non-zero at the surface. We have derived general relations for a 2-dimensional flow independent of the form of the velocity profile, subject to the condition that the incompressibility condition holds. Okay. And based upon that, we get expressions for the boundary layer thickness as a function of the strain rate at the surface for rigid surfaces, and as a function of the tangential velocity at the surface for mobile surfaces. Substitute that into the expression for the heat flux, average over the extent of the domain, and divide by the total length to get an average heat flux, and from that we get the correlation for the Nusselt and the Sherwood number. So, this completes our discussion of forced convection past surfaces boundary layer analysis. Next class we will briefly look at forced convection through porous media, and also forced convection, the Taylor dispersion in a pipe, before we complete our discussion of forced convection. I will continue this in the next lecture on a new topic. I will see you then.